Ladies and gentlemen, the wait is finally over. We're going to finish our epic series here on endurance, fatigue, conditioning, whatever the heck you want to call it. This is where we're really going to dive into the different aspects of physiological pieces that make up conditioning or endurance, or that cause it. Now, if you're new to this video, or you've just stumbled upon this, a friend has shared it with you, or you've caught it on YouTube somehow, I would encourage you to take a quick step back. Go check out the previous videos. There's some in the 5-minute version and some in the 55-minute version. First thing I'd like to start with is number 1, where I talk about my definition of endurance. That's going to be important for later on in this video when we talk about the physiology of different aspects of endurance. That way you know what the hell I'm talking about. You're on the same page with nomenclature, etc. Also, I'm not going to cover programming in this particular video. I've done that in a separate, longer video. All right, so if you want to know the best exercises to select for maximizing aerobic performance, or you want to know the optimal rep range for anaerobic capacity, I've already done that separately. You're going to have to go check those videos out. Okay, once you've done that, then I would encourage you to go on to step number 2, which is the 55-minute video where I talk about what I call how we make cellular energy for exercise. Now that's a dumbed down or coaching-friendly version of saying metabolism, bioenergetics. It is where I go into how you use fat for fuel versus carbohydrate. What are the pros and cons? How you use, from the cell's perspective, fuel from the liver versus the blood versus the muscle itself. What practical implications does that have to why you get tired during certain events and others? So once you do that, now you're really going to understand this particular video a lot more, or a lot better. Because we're going to take all that stuff and we're going to build directly on it. So a lot of pieces in this video might not make sense if you skip particularly that metabolism video or the previous one. But having said that, here what we're going to do is springboard off those first 3 pieces and go into why you actually physiologically get tired. And remember, if you had Phys before, or you had maybe Phys 5 or 6 years ago or something, or you've least maybe you're coaching but you've gone back and read some textbooks. I don't cover this topic like the textbook. I'm not just going to teach you about, well, there's a phosphocreatine system, aerobic system. And I take a more systematic, whole body approach to that. So what I want to understand is why fatigue is happening, because it's not just because of ATP PCR system or glycolysis, right? Or gluconeogenesis, or whatever it happen to be, or glyconeogenesis for that matter. All right, so it's a bigger picture there. We're also going to jump into VO2 max specifically. I've teased about this before. People use this term a lot. You've heard it, but you may not know exactly what it is and what role that plays in endurance training and performance. And then finally, why you breathe. Now, this is interesting because you might be thinking, well, I breathe so that I don't die. Yes, I'll grant you that. But why? Now, you might be also thinking, well, so that I can get oxygen in. Sure, obviously. But why does that actually kill you? What's the actual problem there? I don't think most people really understand that. So that's what I want to get into at the end. And especially because I would say this active breathing field is probably the biggest, most cutting edge stuff happening in all of human performance. So I want to talk a little bit about the research we've done in our laboratory, the studies we've produced, as well as some other resources you can go and learn more about the breathing stuff for performance. So having said that, real quick before we jump in, I want to make sure that we're all on the same page here. I've been getting a lot more people jumping on to these videos recently. And I want to take a quick second to let you know why I do these to begin with. There were several reasons why I created this website a handful of years ago, and why I'll continue to do this with these videos. Well, one of the main reasons is because of probably you right now. So I know a big chunk of you watching this are in my class, one of my many classes. And so what happened was I would notice specifically, or very much so during these metabolism videos, the Phys stuff, in those lectures, those are always the hardest for students. And I just started thinking, like, why is it that the hardest lectures we give, the students don't have any opportunity to take it at their own pace? Some people just had Phys last semester and got an A. Well, they don't need to sit through 4 or 5 days of a really slow pace. Some of you took it 5 or 6 years ago. Maybe you're coming back to school, or you really struggled with it, or this piece was really difficult for you. It wasn't explained well, they went too fast. Why is it that everyone gets it at the same exact pace? It didn't make any sense to me. So some students would run up after class, or they'd want to videotape, or they'd want to record their lectures, and some want extra notes, and I'm just thinking, this is insane in 2019. Why don't I just take the lectures, put it all up there, and students can take it at their own pace. Use the exact same lectures I give, the same PowerPoint. You can watch it as slow as you want, as fast as you want. You could watch it at 1.8 speed and get through it a little quicker for a quicker view. You can go back, stop it. Wait, what did he say again? I kind of dozed off, I spaced off there. Or I didn't get that part at all. I'm going to go back to that quick section. This just made a lot more sense to me. In addition, when I realized that, I started thinking, man, there's probably a lot of people out there that are coaching, that are trainers, that are just super into the field, maybe doing their own workouts, that would love to know this information too. But in order to get it, they would have to get into a university. This is going to cost a ton of money. They're going to have to take 2 or 3 years of prereqs. And I thought that's just all garbage. And so what I've done is put this together in a platform that says, you know what, hopefully, my friends in class, it's helping. And hopefully that you're being able to study and learn at your own pace, and this is increasing retention. And the data I've collected has shown that. People are doing much better on their exams. And those of you that aren't in my class, boy, you get to benefit from that. But in order to make this thing work, the only viable way to make this thing happen is to put some sort of crowdfunding behind it. So what I actually do is I have a Patreon account that hopefully will flash up here on the screen sometime soon. You can see where that is, and you can head over to that, make a small donation. And what that really does is support this for my students. This is what allows me to make these videos. I can send them off to Ryan. Ryan is doing a fantastic job producing them. If you've been a fan of these for a long time, you'll notice the production value is going up exponentially, and that's because I can afford to give Ryan some money here and there and some other folks. So the quality has gone up. I've actually have some real big surprises coming soon in terms of notes and quiz questions and things like that are going to be coming, and that's because people have been contributing some money. So if you're a student of mine, don't even attempt, under no circumstances, make a contribution to this. You've already paid enough. But if you're not, and you're one of the other people out there that are benefiting from these videos and hundreds of hours of free content, if you could spare $5-10, that only goes to my students that I can pay, not my students in this class, my graduate students that I can pay to do other stuff for me, to free up my time to make these videos. So really, the money you're giving me is buying me time, or it's buying me the ability to pay Ryan or somebody else to help out. So enough of that being said, I appreciate the support. If you don't have any of that stuff, no worries, no problem. Help share it around, because there's probably lots of other people that would love to see these videos and don't know they exist. Especially people that maybe are changing careers, they can't afford to go back to school. They're willing to put in the work, they're willing to put in the time, they just want good quality information. The more you share it, the more those eyeballs see it, and the more the world improves our training and nutrition and programming quality. So that being said, let's actually finally dive into the physiology of endurance. Quick backstory here. As I mentioned, I like to think about endurance or fatigue management as going, okay, you know what? Let's think about the entire human body. Go through all the physiology and exercise physiology class, and instead of going system by system, let's just think, well, what are the components, step 1 to step end 20 or 200 or whatever it happens to be, and think, what are all the things that have to go right for me to do human movement so that I can perform well? And then what are all the possible ways each one of these could be susceptible to fatigue or could cause fatigue? And so that's what I really am going to do in this video. You notice there are 6 layers. Now, keep in mind all 6. This is going to come in at the end. In fact, kids in my class, you're going to need to know these 6 very specifically. And so what I want to do is go through each level and talk about what their basic role in performance is, and then how they get fatigued, and then what you can do about that. Quick reminder, though, sorry I keep doing those quick reminders, we're eventually going to get there. Last little piece here. Go back and watch this individual video where I talk about in detail the different types of endurance training. But very quickly, muscular endurance to me is something like, push-ups in a minute, 50, 30 reps, very local to the muscle itself. It's not really like a true metabolic, a cardiovascular fatigue. It's a very muscular, local issue. Inside of that, I go high-intensity endurance. Think of that as like 30 on, 30 off, or intervals. And then we'll talk about long-duration endurance. Now, in the other videos, I split these up into further subcategories, but for now, the way I'm going to approach this physiology section is to think of these 3 really distinct paradigms. So long, steady state, short, high-intensity, really hard intervals, and then maybe like muscular endurance. All right, now again, in reality, I actually, in my head and with my athletes, I split them up into a lot more subcategories. But this is the first level I want to get to. My challenge to you right now, as you're going through this video, if you're thinking, well, I don't do anything that's in only one of these 3 categories, great, neither do I. So as I'm going through this material, start thinking, okay, well, you know what? He's talking about what happens if you did like 30 on, 30 off. But how would this apply if I did something more like my soccer athletes? Or how would this be different for my hockey players? How would this be different for my personal training clients? So yes, I'll acknowledge there are other training windows within that, And you should be thinking about how this would change, what would be different, how this would go up, this would go down. That's really what should be going on in your head instead of just blanket memorizing, oh, there's 3 types of endurance. No, horseshit. That's not at all what there are. There are many, 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 many ones. All right? So think about that on your own, though. I can't do all the thinking for you. So why do we actually get tired is finally what we're going to get to. Remember from the previous video, it's really 2 things. You either run out of energy, which is ATP, or you compile too much waste. And sometimes compiling too much waste stops you from making more ATP. Sometimes not. Sometimes this is separate. But this is really what we're getting after. And in the previous videos, I walked you through a giant slide like this where I took you through all the different macronutrients, how those get in your stomach, what those do in the blood, and where they're stored. And then eventually we walked in through, in painstaking detail, basically all of metabolism. We went through oxidative phosphorylation and glycolysis, and we went through beta oxidation and IMTGs and how we use short-chain fatty acids and long-chain fatty acids for fuel and all these different things, right? And so you should have a basic understanding. I'm going to assume you have this from one of the short videos. I think this particular slide was in a very quick 5-minute video, right? But having said that, we got to move on now. So it's time to actually jump into these 6 different layers. So starting off with layer number 1, in order to have any kind of human movement, that has to start with the neurological system. Could be central nervous system, could be peripheral for sure, could be a combination. Point is, nerves have to tell muscles what to do. And if we understand the metabolism going on at the nerves, we understand this is primarily driven by carbohydrate metabolism. So the nerves, at least in terms of what I'm aware of, can't use fat for a fuel source very efficiently. So if you run low on carbohydrates at the level of the nervous system, we're going to have neurological fatigue. Now that's a whole separate issue. The whole idea of central nervous system fatigue with exercise is pretty overblown, poorly understood. Peripheral is a bigger issue. Nonetheless, carbohydrates are your thing there. Now that doesn't mean you have to be on a high carbohydrate diet or you'll have neurological failure. That's not at all what I'm saying. I am saying that the nerves are going to preferentially use carbohydrate for fuel though. Now, if you remember from exercise phys class, if you didn't have it or forgot, you're going to have to go back and learn this on your own. But the way that we have interaction with an action potential is you have sodium coming in through one side of the cell and potassium going through the other one. Well, in order to get that gradient reset, we have to use the sodium pump, the Na+ pump, to reset that. Well, that itself requires ATP. I know you covered that in Phys. That pump itself, because you have to do something in an active process, you have to reset a gradient. It's kind of like if you were to launch a catapult. Well, in order to cock it back, you have to put energy back in the system to re-crank it so that you can hit one flip and it flies. Right? Well, that takes ATP to put it back in the system. And so that fatigue, that itself can become fatigued. The nerves also have a problem with pH. So if it becomes too acidic or it becomes too basic, and in the case of exercise, acidity is going to be the problem. Because it's going to be functioning on enzymes like everything else, a low pH or high acid will cause the nerves to be compromised in terms of performance. So moving past the level of the nerve, we've talked in depth already about the level of the muscle. We know that it uses phosphocreatine, glycogen, glucose to some level, and fat. But the muscle itself only stores glycogen, right? We store the glucose somewhere else, right? Where else? You know where. Right? So the muscle only stores PCR, glycogen, and fat. In terms of fatigue, then, you can certainly run out of phosphocreatine. That's a big problem. That'll be an issue for certain types of activities. Muscle glycogen, you're not going to necessarily get to 0, but you can become extremely depleted to where the muscle starts sending out signals to stop metabolism. Fat stores in the muscle, otherwise known as IMTGs, it's a little bit tricky to understand what's exactly happening there, but probably going to be running fairly low as well during some types of activities. The metabolic speed, though, is what also controls or regulates fatigue. So sometimes during some types of activity, you're simply not performing well, not because you're out of, say, glycogen or fat. It's just because you can't create speed fast enough. So in the examples we've used before, if we have to start using energy systems that are slower, it's not that we're out of ATP or that we're building up too much waste. It's just that we're not going fast enough because we can't get into the right energy system. So that's what I call metabolic speed. We're just not fast enough, right? Not getting us there. And then, of course, we've talked extensively about how pH is a problem, right? So the enzymes, the machinery that you use to create ATP or to even hydrolyze and split ATP don't function well in extremely acidic environments. So that'll be a problem there. When the muscle starts getting fatigued, it's going to start reaching out to the blood, right? Because the blood is passing right on by it. And it's going to start doing a whole host of things. The job of the blood is to store the glucose, right? So we store glycogen in muscle and in one other place, which we'll get to in a second. We store the glucose in the blood. We also have certainly a lot of fat. We've talked about in previous videos how when we mobilize fat from our arm or our stomach or our leg, and we want to put that into our quadriceps for energy, that has to go in the blood, right? That's that multiple step system where we have to metabolize it, attach it to albumin, put it in blood, etc., move it all the way around. Okay, now, so it's going to have some fat in our blood. The other major job of course, the blood is to bring in oxygen into the cell and to take carbon dioxide, lactate, which is that LH negative, and the H plus, that hydrogen and proton, out. So those three items, carbon dioxide, hydrogen, and lactate, we want out of the cell while we put carbohydrate, glucose, fat, and oxygen into the cell. So when we globally talk about this is get nutrients in and waste products out, the nutrients in are the glucose, fat, and O2, and the waste products out are the CO2, lactate, and hydrogen. Another major role in the blood is this capillary density / blood distribution. So remember, the better I am at getting these products in and out accordingly, the less fatigue happens at the level of the muscle. So when you have muscular fatigue, I don't necessarily know if it's actually the muscle per se or if it's a problem getting clearance. So if I'm having a hard time getting things out of the muscle, it may not be the fault of the muscle. It may be the fact that you have low capillary density or not enough capillaries, so you have no place to where the blood can exchange into the muscle to get this stuff out. So this could be a capillary issue. It really could be a blood flow issue rather than an actual muscle issue. Now, from a practical perspective, you may not ever know without taking a biopsy or doing some imaging. My point being, we can do certain types of training that drive capillary density and enhance it, right? And we'll get into more of this detail with the capillary density in just a second. But moving on to the blood, right? Since we're here, we've got to talk a little bit more detail. So if we look at specifically what's in blood, if you were to go get your blood drawn, they would take it through a centrifuge, spin it all down. It would separate into two major categories. Category 1 is basically plasma, which is 90% water and a bunch of other awesome stuff. But for the purposes of right now, we'll just think of that as water. And the other component are the red blood cells. And you notice of all that total blood, about 50% of it is red blood cell, about 50% of it is water. Well, the numbers are actually a little bit different than that. And we call that the hematocrit. So keep in mind, a major mistake I hear with hematocrit all the time is hematocrit is not a number, an absolute number. It is a percentage. All right? So I'll say that one more time. Hematocrit is a percentage. It's going to come in handy in just a second, and certainly in my class. So the percentage of your blood that is red blood cells is your hematocrit. So in men, it tends to be around 45, 46%. In women, it's a lot lower for a whole host of reasons. Okay, now you can manipulate your hematocrit, but it gets deceiving, right? And so we have to break this number down a little bit. What I can tell you is some athletic agencies have regulations on hematocrit. And so in other words, if you're normally 46% and you show up to a race at 55%, that is an indication you have likely blood doped, because blood doping is often taking this exact formula, dumping out the water, harvesting a bunch of those red blood cells, waiting for your body to rebuild that normal storage back up, and then taking those extra red blood cells and jamming them back into your blood. Now, we know red blood cells carry all of our oxygen. So if I do that, my hematocrit goes way up, my performance goes up to an extent. But if I'm normally at 45% and all of a sudden I'm at 55%, especially very quickly within a matter of weeks or something, I very likely have injected red blood cells back into my own body. Right? And so this has been going on a long time with endurance sports, and testing is very good. It's hard to get away with it now, but that's a classic thing that you would do with blood doping, one of the original methods of it. Right? Well, the point being, the hematocrit changes with training are a very common adaptation. So, the question I have for you now is, would increasing blood help endurance? In other words, do you think with chronic endurance training, and it really doesn't matter if you're doing the high intensity stuff or the long duration stuff, probably not muscular endurance though, If you're doing those types of training, would you have more total blood, say after 8, 10, 12 weeks of training? Would you have more total blood in your body? Would you have a higher red blood cell count? Would you have a higher hematocrit? So these are questions I would expect you to be able to answer very, very confidently. So what are they? Yes, no, not sure. Well, here we go. So not only do you increase total blood, it's probably the single biggest and most important adaptation to any type of endurance training is to have more blood. Certainly anything from that high intensity interval on to long duration or anything between that. Having more total blood is huge because it allows you to carry more red blood cells. If I simply had more red blood cells but my total blood didn't go up, as you can see depicted here, my hematocrit would be really high, but the problem with that would be my blood would be way too viscous. It would be too thick. So in order for me to be able to handle more total red blood cells in my blood, I have to match that with an increase in water. So my hematocrit might go up a little bit, or in this example here, the hematocrit technically went down a little bit. But if you look at the numbers, so in the pre-training example, this individual has 5 total liters of blood, and 2.2 of those liters are red blood cells. So 2.2 divided by 5 is 44. Well, after training, they now have 5.8 liters. They've added almost a full liter of additional blood. Now, their hematocrit went down because they added more water than they did red blood cells, but look at the absolute amount of red blood cells. Pre-training, there was 2.2 total liters of blood cells in the body. Now there are 2.4, so he has added 0.2 liters of actual red blood cells. So even though his hematocrit didn't change, he had more red blood cells, and that's what matters. So having more total blood, which allows you to have more total red blood cells, is a critically important adaptation for virtually any type of endurance training. So what happens, and this is very, very, very helpful, again, it allows us to carry more more oxygen, which means more oxygen delivery to the tissue. And this is a very, very, very good thing. All right, so if I were to ask you again, does total blood go up? Yes. Does the total amount of red blood cells go up? Yes. Does hematocrit go up? Well, it typically does, but you could argue maybe it doesn't change or it goes down a little bit, right? But the general answer is yes. So even though this example shows it going down, typically it goes up. But even if it didn't go up, it's not the worst thing ever, because too much red blood cells in the blood without an increase of water means too thick. Too thick of blood pumping through you is kind of like sludge, and it's not very effective. So you really don't want much more than 50, 52% at the highest anyways. From there on, you just want more total blood, not necessarily just jacking in more red blood cells. Okay, so hopefully that was clear. In terms of capillary density, here's what these things are. You know that what your aortas and your veins do, right? Or aortas, your arteries and your veins do. Arteries go away from the heart. Typically are oxygenated, but not always. Veins go back to the heart. Typically deoxygenated, but not always. There's one particular example when it goes to the lungs and stuff that throw that all out. But the difference, arteries go away, veins go back. So the difference between an artery and a vein is the muscle. In other words, arteries go away from the heart, they go to a muscle, arteries turn into capillaries, capillaries surround muscle tissue, they leave the muscle tissue as a vein and go back to the heart. And the reason we do that is because you can have one giant artery going into a muscle. We split that up in a whole bunch of tiny little distributaries surround the muscle. Now, the reason we do that is to enhance our gas exchange. So when I take a single venule like that, and I split it up in a whole bunch of thousands of tiny little ones, what happens is a basic pressure equation. It would be like if you had water going through your hose, and all of a sudden at the end I split it up into a whole bunch of little tributaries. Well, because there's so much more area, the pressure goes way down. And so the flow of the blood through the area goes way down. Slower blood flow past your muscle increases the time you have to get the nutrients in and the waste out. And so blood comes rushing into the muscle, gets split up into the capillaries, sort of slows down, and by the time it finishes those, it goes back together into a vein, the muscle contracts and shoots it back up out. Okay, and so this is another reason why enhancing capillary density, just like that, improves performance, right? Because number one, it allows more places for gas exchange, more complete coverage of all aspects of the muscle, and as well as it slows down the transit time, the amount of time that the artery or the capillaries go past the muscle is really, really increased. So the time is increased, the speed though is slower, which is the same thing, right? So we have more gas exchange. So it looks like something like that, right? So it's red kind of coming in, and the more of these exchange sites I have, the more likely it is to be blue or deoxygenated going out. All right, somebody who is more fit or better at this stuff is better at extracting all of those nutrients on the way through, and they don't leave any left for waste, right? They're also better at getting the waste products back out. So if we go back to our list here, or our slideshow, hopefully you understand that blood aspect a little bit more. Now, in the previous videos, I talked about what happens when the muscle starts running low on substrates, particularly carbohydrates and fat. It's going to reach out to the next thing that holds these or stores these, which is the liver, right? So the liver stores glycogen. So to recap what we said earlier, the muscle and liver store glycogen, the blood stores glucose. So the muscle starts exercising, it starts running low on its glycogen. It reaches out and starts stealing glucose from the blood. Well, that's a problem, right? Because if blood glucose gets really low, blood sugar, another way to say it, you pass out. Why? And this is a critical part. Why does that actually happen? Well, because the brain's primary fuel source is glucose. And so the endogenous reaction of your body is to say, hey, look, blood glucose is getting really low. We're going to have a problem upstairs. I don't care how bad you want it, how mentally tough you are, I'm taking you down. And boom, you pass out. You go down. It stops you from exercising because it needs to preserve the brain. Right? The brain takes a huge chunk of your basal energy. It goes down or stays the same during exercise, but the total expenditure of energy goes up. Right? So the brain is a real big problem. Well, in order to not let that happen, the liver says, wait a minute. I'm kind of like the backup system for the muscle glycogen. So the liver is huge, right? It's right over here. It's a really big ass organ, massive, and it stores a ton of glycogen. Well, relative anyways. It stores a ton relative to the blood. Not as nearly as much as muscle, and not nearly as much fat as you store, not even close, but it stores a lot. And so you start exercising, muscle glycogen gets low, you start taking glucose from the blood sugar starts getting low, liver starts going, oh, whoa, I got you. Let me split up some of this glycogen, kick it into the blood as glucose, and I will make sure that while the muscle keeps burning muscle glycogen and muscle glycogen levels start going down, blood glucose stays the same, or in fact, what you typically see happen during exercise, blood glucose levels go up. Well, that's all great until the glycogen in the liver runs out. That's your backup system. Oops. So what happens when the liver starts running out of its own glycogen? Well, now we start seeing the wall. We start seeing a true bonk, right? When the signals start coming from the liver that says we are out of glycogen, you start having problems. So in our sports nutrition class, we'll certainly talk about then supplements you can take during exercise, or nutrition during exercise or pre-exercise, maybe even the week before, to start combating this. But that's the basic physiology. The other thing you start doing is reaching out to the adipose tissue. So this is actually what fat looks like, by the way. And if you're doing something where you can use fat as a fuel source, you'll start taking stored fat from the adipocytes, the fat tissue, putting that into blood through the system we've already talked about at length now, moving that in, and then we'll start transporting whether it's the glucose or the fat and bringing that up into muscles. So you can see the arrow from the blood back into the muscle tissue there. Now, unlike the liver, you're basically never going to run out of fat, stored fat. So even someone who's 3% body fat still has way more body fat than they'll really need for virtually any type of exercise. So there's no limitation there. The downside, of course, is not that it's going to run out, but it's just too slow. Right. So, of course, glycogen may be much faster. That'll be the preference. Okay, moving on from that, though, we kind of have to take a little sidestep. So going back in the blood, we got to talk about what regulates actually the blood getting through. So we talked about capillaries, and that's going to help us determine how effective we get what's in the blood into the muscle. But how effective we get the blood around the body is actually a heart issue. And so we'll start talking about the heart a little bit here. Its job is to circulate blood, of course. And the two main things we need to be concerned about are heart rate, of course, how often I'm pumping, and what's called my stroke volume. So the stroke volume is appropriately named. It is the amount of volume of blood you kick out per stroke or per contraction. So if I know how often I'm contracting, and I know how I'm kicking out per contraction, I can calculate exactly how much blood I'm kicking around the body. Well, I know you know what happens with heart rate, with training, and with exercise, but stroke volume may not be as intuitive. So let's take a quick second to review some cardiovascular physiology, or heart physiology nonetheless. So the intrinsic rate of the heart is actually a lot higher than what you think. So what you're looking at the bottom is heart rate, or beats per minute. And what you see is the actual intrinsic rate, so what the heart would like to beat at, is actually closer to like 100, 120 beats per minute. Now hopefully none of you are watching this video and your heart rate's 120 unless you're just super excited, and to which I would say if your heart rate is this high watching this damn video, you need to kick in like $500 to Patreon. That's ridiculous, right? You shouldn't be that excited. Okay, well, your heart doesn't actually beat there. A normal person is going to be beating 60 to 80 beats per minute. A decently trained athlete, maybe 50. A really well-trained athlete, 35, 40, right? Getting in the low end. And so what you actually do is you have a nerve that drips down onto your heart called the vagus nerve. Not the vagus like the V-E-G-A-S. It's the V-A-G-U-S, the vagus nerve. And the vagus nerve activates what's called the parasympathetic nervous system. Okay, so if this is actually slightly opposite, because you remember from skeletal muscle physiology, in the skeletal system, if you transmit acetylcholine, that causes muscle to contract, right? Well, when you leak out acetylcholine from the vagus nerve, it actually causes the heart to slow down. It inhibits contraction there. So the vagus nerve submits that or releases that acetylcholine that activates the parasympathetic nervous system, which is your rest and digest, right? And that actually slows your heart rate down. And that's why you're sitting in class or watching this video right now and you're like 80 beats per minute, you're inquisitive, you're not asleep, hopefully, right? Or awake, and you're fine, you're not tired there, but you're not also like that, right? You're not ready to go at 120. If I want to put you to sleep, or if you're watching this video post-lunch or something like that, and you notice oh boy, this one's going on, right? What's happened is the parasympathetic nervous system has picked up or increased its activation, and you've gone from there down to there, right? So obviously you realize your heart rate goes down when you go to sleep, right? It slows way down, you get super, super tired. Now this is something we could take maybe in a separate video, but you need to be able to understand this because there's lots of tricks you can use with your athletes or your clients to help them get into parasympathetic. I would recommend checking out Jill Miller and Yoga Tune-Up, Brian McKenzie, Art of Breath, XPT, PJ Nestler. A lot of people have a lot of good tricks and tips about how to get an athlete parasympathetic. And in fact, a little spoiler, there is actually really decent data that shows the faster you can get into parasympathetic post-workout, in some cases, the adaptations to endurance specifically are enhanced. So it's probably not a good idea to do like a 45-minute blast, throw up, oh my God, I'm dying, so exhausted workout, and then go right back to work. You probably need to spend some time getting recharged back into parasympathetic, getting turned back down before you then go back to work or go see your kids or whatever you have to do. But nonetheless, and again, another spoiler, you can just simply do this with regulating your breath. But you'll have to go to those other sites, or maybe I'll make a video about it. Let me know. Yeah, I'll have to hell with it. Let me know if you want to see a video like that, and maybe we'll make one. Nonetheless, you're down at 35, 40, you're cruising, you're kind of sleepy. Well, in order to get back up to 80, you don't have to add adrenaline. You don't need to take caffeine. You just simply need to back off the throttle from the parasympathetic nervous system. So you take your foot off the brake there a little bit and you'll go right back to there. You take your foot off the brake even more and you go actually up to 120. So here's the analogy I give. Imagine you're in a car going down the hills of San Francisco. The parasympathetic nervous system is your foot on the brake. You want to slow down, you push that brake even farther. You want to slow down more, you push it even farther. Oh, but now you want to go a little bit faster? I don't have to hit the gas pedal. I just take my foot off the brake a little bit. You want to go faster? I take my foot completely off the brake. And now I'm actually going faster than I would like to go, 120. Okay, now I'm going down that hill. I'm going as fast as possible. I'm not touching the brake at all, but that's not fast enough. I want to go faster. Well, now I can hit the gas a little bit. And the gas is the sympathetic nervous system. So that's how we regulate our heart rate, right? So we can go from 120 to up to, say, 200, depending on, all kinds of other factors. Most people have a max heart rate of somewhere between 165 and 210, 215, right? I've routinely had mine 210, 215. I know the math, trust me. Those estimation equations, 220 minus your age, they're just random equations. They're not incredibly accurate to the individual. I've had extremely high-level endurance athletes with a maximum of 170, and I've been at 210. I think the highest I've gotten is 213, and I'm not even close to what I would call a high-level endurance athlete, right? So it's really physiologically depends on the person. My point being, it's that vagus nerve that can withdraw its acetylcholine, and or we can hit you with some adrenaline, and we can up-regulate, down-regulate our basal heart rate. So here's what happens. Heart rate goes up. We're contracting more. This increases blood flow throughout our entire system, right? Well, because of that, we have an increase in what's called venous return. So this is the amount of blood coming back into the heart from the venous system. So it contracted, went throughout the body, and it came back up. The more I contract, the more I send out, the more comes back up into it, right? Basic pendulum. Farther I push it, farther it's going to swing back the other direction. So that increase in venous return means we have more blood slamming into the heart on its way back in. Now, in my class, we've talked about in the last couple of sections, what happens when I put an eccentric stretch on a muscle? You eccentrically stretch something, in fact, especially when you eccentrically stretch something really quickly, stretch shortening cycle kicks in, and simply the elasticity of the tissue kicks in, more appropriately in this case, the elasticity of the tissue, and the more you stretch it, the faster you stretch it, the faster it wants to contract back. So by increasing your heart rate, you've increased the blood flow, you've increased the amount of blood smashing back into the heart. That eccentric stress on the heart increases the contractility of the left ventricle. That then causes the left ventricle to contract with more force, therefore enhancing or increasing stroke volume. It's just like your hamstring or your pec or anything else. If I give myself a big, strong eccentric contraction of my pec will respond by contracting harder and faster. It's exactly what your left ventricle is doing. You're slamming more blood back into it. It gets a big stretch. It responds by contracting harder and faster. In terms of the heart, how hard we contract, how much blood we kick out per squeeze is called our stroke volume. It's kind of like the strength metric of your cardiovascular system, or specifically the heart. Okay, so as I'm working out and I'm exercising really hard, my heart rate's going up. Well, I'm also elevating my stroke volume. If I take that stroke volume, how much I get out per squeeze, multiply that by how many squeezes I'm getting per minute, I get what's called my Q, or my cardiac output. So if both of those things go up, my cardiac output goes up. And this is a huge driver of endurance performance, enhanced cardiac output. It helps acutely and it helps chronically. All right, so again, we have two ways to get that. Higher heart rate or more stroke volume. Now, there's not much you can do about your max heart rate, but you can see significant improvements in your stroke volume with training. So with chronic training or chronic endurance training, we do see an increase in the left ventricle size, and this is the good stuff, right? This is not a reduction in chamber size. So the interior chamber where you store the blood does not go down. That's the bad kind of heart adaptation. That's the bad kind of hypertrophy. This is the chamber stays the same or gets larger, but we thicken up the outside of the left ventricle, which means we put more muscle mass on it, right? We put a bigger glute muscle on there, but we don't shorten down the muscle or anything like that, right? I don't know what that was. Sorry, little model kick my ass out demonstration. But nonetheless, left ventricle size goes up in a good way. Left ventricle strength, again, the amount of units of force it can produce, goes up. These things combined increase the stroke volume, and because of that, heart rate goes down. So to recap, when I'm exercising really hard, my heart rate goes up, and my stroke volume goes up because of that venous return. That makes cardiac output go up. But at rest, you've gotten that chronic adaptation, you've gotten that chronic hypertrophy, and you've got that chronic increase in left ventricular strength. So even resting, My stroke volume is increased. Because I'm kicking more out per pump, I don't have to pump as often. And so that's, folks, what allows what you all know to be true, in that the more trained you are, the lower your resting heart rate. It's generally mostly because you have more blood. Because of that, you have a greater venous return. The increased venous return helps you build up the strength inside the left ventricle, so you kick out more blood per pump, so you don't have to pump as often, right? And that's the physiology behind why your resting heart rate goes down with chronic training. Again, this doesn't really matter if you're doing high intensity intervals, you're doing long duration stuff. I'm not saying they're identical. I'm saying they both would cause this adaptation. Probably not the muscular endurance stuff, certainly the anaerobic capacity stuff, the aerobic capacity, and long duration, steady state stuff. All of those are probably going to give you good adaptations in this area. So that being said, I've basically given you now the equation for VO2 max. This is the maximum volume of oxygen you can bring in and utilize. I just haven't been explicit about it. So this is what the equation is. You can look it up on your own. I've color coordinated them for you. So VO2 max is really Q, which is how much blood you pump per minute. We've talked about that. Multiplied by what's called your AVO2 difference. And that's a fancy way of saying how much oxygen the muscle steals from the blood. So A being arteries, veins being vesicles, it's O2 difference. That number literally is calculate how much oxygen is in the arteries, fully oxygenated. Let's say that number is 10. I'll say the number is 8, just to make that math nice. You have eight oxygen molecules in the artery, fully oxygenated, 8. It goes by the muscle. The muscle takes some of the oxygen, right? Then we have the vein. Well, how much is left in vein? So if there's 5 left in the vein, there was 8 going in, there's 5 left. So what's the AVO2 difference? 8 minus 5 is 3. So you have extracted 3 of the oxygen molecules in the muscle. It's not a very good ratio. If I got you trained and we worked really hard, now when 8 went in, now maybe only 2 come out the vein. So my 8 minus 2 is now 6. My AVO2 difference increased because I was better at taking oxygen out of the blood. Now, you're all so damn smart. I know you see where this is going. How was I able to get better at taking more oxygen out of the blood? That's right. I increased the number of capillaries. See how this stuff all works together? Right? So, if I want to improve my VO2 max, which is my ability to bring in and utilize oxygen, it's my maximal aerobic capacity, I need to understand, well, how much blood am I bringing in and pumping around the body? And then how good am I taking out that oxygen into the muscle? All right, so you can see the equation at the bottom there. Another way to think about this, the Q being cardiac output, is simply the heart rate multiplied by the stroke volume, which we've already been over. And so this is a classic example of what's called the Fick equation. Okay, and what I've shown you at the bottom are the arrows with what happens with chronic training. So we know without question, VO2 max goes up with training, and a good chunk, 20% or more in a year of training, if you can, maybe a couple years, depends where you're at, right? Obviously, the more trained you are, the less improvement you get. In terms of numbers, I think it's actually probably pretty good for you to know. Most kind of like untrained college men will be in the 40s or so for their VO2 max. Women a little bit lower, 35. A lot of my MMA fighters are between 55 and 65, typically closer to the 60, 65. But a high-level endurance athlete, like a true steady-state endurance athlete, they may be 70, 75. People have been as high as 90, 95, getting close to 100, some of them. But the point is the VO2 max will certainly go up with training. Stroke volume at maximum will go up, like we talked about. And so will the AVO2 difference. Now, not much, but it will go up because you'll have more of those capillaries. Don't get tricked here. Like 20, 30, some percent of the people in my class are going to miss this question. Heart rate, though, doesn't go up at a maximum. Remember, it's simply determined kind of by your age, so that doesn't go up a ton. We'll get into the fatigue of this and why this happens later, but maximum heart rate doesn't go up. Maximum stroke volume up, maximum VO2 max up, maximum AVO2 difference, and because of that, like I said, our VO2 max goes up. I've also summarized this in a nice chart for you if you just kind of want to conceptualize. And what I've done is I've shown you all those variables and what happens at different things. So what happens at rest, what happens at submax, and what happens at max. So hopefully you can work yourself through a chart like this and be able to identify what's going to happen at all three different areas. So if we look at the actual anatomy of the heart, you don't have to know it in my class, but I think it is important. You should understand all the valves and ventricles and veins and what they do. Well, what causes fatigue or the waste products associated with the heart, number one is it's almost entirely a slow twitch muscle. In fact, the slow twitch fibers in the in the heart, are even more slow twitch than those in your skeletal muscle. So it is primarily a super slow twitch muscle, which means it's not going to be able to generate energy really, really fast. But the primary limitation here is the time it takes to fill the ventricles or the arteries. So remember earlier when I said your max heart rate doesn't go up with training? Well, that's because it's limited by your ability to fill the time. So if you are contracting every second or so, there's plenty of time when I'm not contracting to fill up the ventricle so I can squeeze blood out. But if I'm contracting, I won't do it just so I don't blow your ears out, but if I'm contracting at a super fast rate, that leaves no time to actually fill the ventricle with blood. Because you have to remember, blood comes in the right artery, goes in the left ventricle, squeeze out of the left ventricle, you go to the lungs. Comes back from the lungs with fully oxygenated, goes back into the left artery, goes in the left ventricle squeezes it out and goes all the way to your blood fully oxygenated, right? Well, if I'm spending so much time contracting that I'm basically in tetany, then there's no time for that left ventricle to actually fill up with blood. And so that pace turns out to be right around 200 or so beats per minute, and that goes down with age. And so you don't really want to exceed that pace because you'd actually lose your stroke volume because you would actually lose the amount of blood that gets back into it. So that's not really a good thing. So in terms of fatigue at the level of the actual heart itself, it's pretty much limited by the stroke volume because it's either weak or it's small, or because we don't have enough venous return, because we don't have enough blood, or because we don't have enough time to fill. Okay, so hopefully that section makes a little bit more sense now. Now to really round us out, we have to go to our last piece, which is number 6, and that's the lung. So the point in terms of performance here of the lungs is to inhale oxygen and exhale carbon dioxide. Now go check out the physiology of fat videos, the 5 and the 55-minute ones, if you want to know exactly what the heck's going on there. In addition, hopefully that CO2 piece makes a lot more sense now that you've been through the metabolism and how we make energy 55-minute video as well. Right? You realize the end product of all metabolism, regardless of whether it's coming from fat, carbohydrate, or anything else, it all ends up as ATP, which we use for energy, water, and CO2. And then whew, that all comes out, right? All of our waste goes out in our breath. But the other component here to the lungs are the inspiratory muscles themselves. So if we understand how the actual ribs work, we understand those actually need muscles to contract as well. And those are susceptible to fatigue. So if we look at the lungs really, really quickly, I'll finally get to our question here, which is why do you actually breathe? Well, it's to bring in oxygen, yes. But the reason you actually bring in oxygen, the only reason you care about it, is because you have to have that to produce ATP. It's not about oxygen. Oxygen is not a fuel. It is not a fuel. If you think, oh yeah, it is, because if I try to light a fire and there's no oxygen, a fire won't start. You're correct. It is a requirement for scalable energy production. But if you're burning something, what's the actual fuel in the fire? It's the freaking thing you're burning. It's the wood, it's the house, it's the paper. That's the substrate, that's the fuel. It's my fat, it's my carbohydrate. It's not the oxygen. I need the oxygen because I have to have something I can bind to the free carbon to make CO2. Remember, whether I'm burning fat or carbohydrate, I'm breaking a carbon bond. That gives me energy to make ATP. But then that carbon's floating around. There's an acid problem there. There's a transportation problem there. So the body won't do that. Biology won't do that. Chemistry won't do that unless we've got a free oxygen that's available to bond to it to make it as CO2 that we can release as energy. So the only damn reason we breathe is so that we can manage our carbons. We can get rid of those damn things so that we can make ATP. If there was some way that you could make ATP sans any oxygen, you would never have to breathe. No problem there, right? So that's why you actually breathe. It's an energy issue. not an oxygen issue. But getting back to physiology, we have intercostal muscles, which are these tiny little muscles that go in between our ribs. And then we've got a diaphragm that sits right below our rib cages. You can see in the diagram there. Well, this is a pressure issue. So we know that there's a relationship between pressure, area, pressure and area, right? So if I increase the area, that decreases pressure, right? Because now all the things that are packed into this much area, I give them this much area, things spread out. The opposite happens if I condense the area, too much pressure happens. Well, the only reason you exchange gas with your environment is because of a pressure gradient. I know you've all heard that there's less oxygen at elevation. That's hot garbage. It's not true. I don't care how many times Joe Rogan said it. It's not true. There's the exact same amount of oxygen at the top of Mount Everest as there is in Las Vegas. The difference is the pressure gradient. So when I open my mouth right now, if there's a difference in pressure between the outside world and the inside of my lungs, then things will move until I equilibrate that pressure. Well, in terms of your body, you have oxygen and you have CO2. In the environment, same exact thing, plus nitrogen. Well, it turns out, in my body, it's the exact opposite ratio of those things as there is in the environment, basically. So when I open up my mouth, those two things exchange. Example, when I open up my mouth and I have a lot of CO2 in my blood, and I have a little amount of oxygen, and I open my mouth and I expose it to the environment where there is a little tiny bit of CO2 and a lot of oxygen, oxygen wants to run back into my mouth and CO2 wants to run out of it. Okay? When it's the opposite, I go, and I breathe in, I contract my diaphragm, which goes down, I contract my intercostals, which opens up this whole space. So what happens, the pressure in my lung cavity, it actually becomes a lot lower than the pressure in the environment. So it's high pressure outside, low pressure inside, airflow goes in. Well, the problem at elevation is the pressure in the environment is super low. So even though I get a really low pressure inside of my thoracic cavity, all I'm doing is really matching it to the external environment, and so gas exchange doesn't really happen. So you've got to work really hard to actively suck in the air. When I go below sea level, there's a ton of pressure, super pressure outside, so I only have to make a little adjustment, increase the area of my thoracic cavity a little bit, and then air goes flowing in. But once I've done that, right, so the active process, I've used ATP, I've used carbohydrate metabolism in my intercostals, for fat metabolism. I contracted that muscle, opened up the area. Well, the exhalation is passive, right? So I don't have to contract anything, I just have to relax the muscle groups. That smashes the area, that creates a lot of pressure in the thoracic cavity. So when I open up, the pressure is now higher in my thoracic cavity, lower in the environment, so air goes. Well, during exercise, the inhalation is still an active process, but at max exercise, I need to get that carbon dioxide out faster, and so I make the exhalation process active. I start squeezing and contracting, right? Squeezing and contracting, and trying to put that stuff together, right? Pull my diaphragm up, pull my diaphragm down. Now, we don't have the time to get into it in this video, but this is a huge component to performance. We have shown in our laboratory, and many others actually, this is actually extensive in the literature. I didn't believe this at all until I looked into this evidence base, and it's really well defined. You need to train your intercostal muscles and your diaphragm, and you need to warm them up, just like you would train your hamstrings and you would train and warm your hamstrings up prior to squatting or sprinting. So there's a whole bunch of ways you can do this. I think the best way that I have seen so far is simply to practice nasal-only breathing. So by shutting your mouth, you restrict airflow. That causes the diaphragm and the intercostals to have to work a little bit harder to get in air and to get out waste products. So I think that's a really good way to train yourself. So that's my first recommendation. You want to know more past this, you got to dive into the folks' material who are experts in this area. But we've shown in our lab just an acute warm-up of the intercostal muscles can have a significant improvement in your VO2 max, for example, or anything else. Training has a very good carryover to them. So there's a lot of ways you can explore this, right? So I wanted to bring that up. I wanted to explain in class before, we've gone over the physics of diaphragmatic breathing versus chest or clavicular breathing, right? And if you're not in my class, the quick answer being we want to breathe through our diaphragm for these reasons, not through our chest. All right? And then again, I've also explained nasal versus mouth. I actually like a lot what Power Speed Endurance does in terms of their 4-gear system. I think it's magnificent. Check that out. But we should probably be able, unless we're a professional fighter like Zoila Frosto, and we got about 17 broken noses, and you can't breathe through our nose at all. But for the most part, we should be able to produce some sort of, at least basal, as we're walking around in class, taking notes, as we're walking the dog. We should be able to function most of our breathing through our nose, right? There's pros and cons of both nasal and mouth breathing, but this is some important stuff that we're going to actually play with in class. So that being said, this is, as I mentioned at the beginning of this video, this is an actually a booming area of research as well as application. So I'll be excited in the next few years to come back and take a look at some of this breathing stuff. But nonetheless, we've now covered all of the 6 different physiological systems that play a role in endurance or fatigue or conditioning performance. So what I'd like to do now is to make sure that you understand each type of endurance, the 3 that I have laid out /4, and all of the thousands of other ones I haven't talked about, have a very specific point of failure, somewhere 1 to 6. I told you at the beginning of this video, you need to understand 1 through 6. In fact, most of these things have multiple places of failure. So my challenge to you going forward, think about the type of training workouts you do. Think about the athlete's demands. And think through all of these systems and go, you know what, I bet when I do this type of workout, I'm probably seeing fatigue at the level of the nerve, muscle, and maybe blood, but not the last 3. But this type of workout, really, it's all about lung fatigue and maybe the cardiovascular system. But muscle, I'm not running out of glycogen, or the nerves aren't becoming depleted or getting excess acid buildup or anything like that. So think through that. Again, I don't want to teach you the details of every single type of exercise with this six-part system. I want you to think through all this stuff. So my challenge to you, my homework, if you will, is to go through a slide like this or add extras. Please add extras. Think about what you do and add more. And think about, okay, if I'm doing like a max power thing or a max strength, 1 rep max vertical jump, go through each one of those 6 individual systems and think, where are they failing and why? Do the same thing for, say, hey, max repetitions at 50% of your 1 rep max squat or bench or dead or whatever. 1 through 6. Where's the failure and why? If you're in my class, this is an actual homework assignment. So the next time we meet in class, you need to go through all 4 of these endurance examples, and you need to go through all 6 systems and talk about where all the possible points of failure of all 6. So I'll give you 1 here as an example. You're lucky, listeners at home. I wasn't going to give you any of this. But to make sure my students understand this assignment, let's go through interval training. So imagine you did 30 on, 30 off. And we're going to go through each one of the 6 places of failure, the 6 physiological systems. So I'll start you off with number 1. This is the nerve. Well, if you're doing intervals, you're going to run low on carbohydrate in the nerves. You're going to have a hard time with the sodium-potassium pump. That will fatigue. And you're going to have pH issues. So for number 1, for intervals, I just said, hey, all 3 of those things we talked about, they're all susceptible to failure during intervals. Level 2, which was muscle, right? You're going to run low on phosphocreatine. You're going to run really low on muscle glycogen during intervals if you do enough of them. You're going to have that metabolic speed issue, right? Because now we're trying to create things fast. And you'll have a pH issue. Are we going to run low on fat? No, not at all, right? So that's not on my list. I went through the 4 things that were applicable to this type of training. Number 3, right? Now we've moved on past muscle and we're into blood. Well, it's the same thing. We're going to have the same problems there with the exception of fat. Again, one of the things that the blood can do is transport fat in and out the cell. Not really applicable here unless we did like 100 rounds. But if we did 30 on, 30 off for 5, 10 rounds, fat's really not a player. The metabolic speed is too fast. And so we are limited by the other things we talked about, which is getting carbon dioxide out, getting lactic acid out, getting oxygen in, getting carbohydrates in. We may start to see some depletions in blood glucose. Liver glycogen may start to get low if we do enough rounds, etc., right? Do I give you the short answer here just so it fits on the slide? But in my class, again, go through all the points for each 6 system and finish it. And I'm not going to give you the rest. I'm not going to go through 4, 5, and 6. So the homework you'll turn in, we'll go through 1 through 6 for 1, 2, 3, all 4 different categories. If you're at home, not in my class, I still think you should really do this. In fact, I would love for you to do this and then tell me what your answer is, and maybe I'll let you know if I think you're right or not. I'll give you a hint. As you saw here, many of these different types of training have multiple places of failure, but not all of them have all of them. So one example on the board here only has 2 spots of failure. Another one has all 6 spots of failure. Right? So hopefully you enjoyed this video. This was a long series. This is a lot of work to put together. I appreciate the support. As always, subscribe below, please. That helps me out. This project is a viable thing to do. Support, share. Please share on Facebook, on Twitter, on Instagram, anywhere that you see viable. Open up your old MySpace page, put it back up there so Tom can see it, or whatever the hell that guy's name was. But yeah, keep helping me make these things viable. The bigger I can grow this thing, the more people can see it, the more people realize they can use it in their classes, whatever they're going to use it for. My students benefit, you at home benefit, and we get improved learning, we get improved interaction, and we get this whole thing moving forward. So thanks a lot. Cheers.